In this video, we're going to be talking in more detail about the definite integral. So let's have a quick recap of the difference between definite and indefinite integrals. A definite integral is an integral that has numbers on the top and the bottom of the integral like this. And what the definite integral gives us is a number. So the way we go about computing this is we find an antiderivative for our function. So for our function, we're x cubed plus 1. Our antiderivative would be x to the fourth over 4 plus x. You don't need the plus c when you're calculating a definite integral, but you do evaluate your antiderivative at the top number and then at the bottom number, and you just subtract those two to give your final answer for the value of the definite integral. On the other hand, an indefinite integral is an integral that has no numbers on the top and the bottom, and your answer is going to be in the form of a function. So you find an antiderivative for your integrand, which would be x to the fourth over 4 plus x, and you always write plus c for an indefinite integral, because what an indefinite integral calculates is all possible antiderivatives of your integrand. So in this video, we're going to be concentrating on definite integrals. So this situation up here, and therefore all our answers are going to be numbers. And in particular, what we're going to be focusing on is definite integrals where the substitution method is required. So we're going to get more practice with substitution, and we're going to get more practice with definite integrals. So we are going to evaluate the following definite integral, and the idea is to do a substitution. So thinking back to substitution, we're going to let u be the quantity that's being raised to a power. So that would be x cubed plus 2. Once we've got that, then we need to find du. So we could say du by dx is equal to 3x squared. Or you could say du equals 3x squared dx. So you can get into the habit of doing this part in one step if you like. Therefore, we've accounted for everything in our integral, because this stuff here is going to be u to the fourth. And if we think of the 3x squared as multiplying with the dx, those guys together are going to give us du. But the new problem that we haven't faced before is what to do with the numbers on the integral. So the idea is that these numbers are x values. So we need to take x equals 0 and x equal 1, and we need to turn them into u values. And the way we're going to do that is we're just going to look up here and figure out what our function u is. Well, u is x cubed plus 2. So if we plug x equals 0 into u, we get 2. And if we plug x equal 1 into u, we get 3. So these new numbers here are going to be the numbers when we rewrite our definite integral. So now we're ready to rewrite the integral from the problem. The numbers are no longer 0 and 1, now they're 2 and 3. And let's rewrite our integrand. So this fourth power that we're seeing in the integral, that's going to become a u to the fourth. And the 3x squared times the dx becomes a du. So we have successfully rewritten our entire integral, including changing the numbers over to u values. Let's find an antiderivative. We'll go u to the fifth over 5. We don't need a plus c because this is a definite integral. We will evaluate at 3 and then at 2. So plugging 3 in here, well, 3 to the fifth is 243. So we've got 243 over 5, and then we subtract off the value when we sub in 2. So that would be 32 over 5. And here's our final answer coming up. So 211 over 5 is our answer. So one critical step in this problem was changing the x values over to u values, which we did right up at the top of the screen here. There is an alternative way to solve the problem without changing your x values over. So I'll show you this alternative way just in case you prefer this method. So I've just recopied the integral at the top of the screen here so that we don't have to do too much scrolling. So an alternative way to do it, you would have made the same choice for u, and you would have in the same way figured out that du was 3x squared dx. So then you could say, okay, I'm going to rewrite my integral, and I'm going to say the integral is the integral of u to the fourth du, just like before. But if I don't feel like changing the x values over into u values, what I can do is I can write x equals 0 and x equal 1 here. It's definitely not okay to just write 0 and 1 because that would imply that those are u values. But if you write x equals 0, x equal 1, that's perfectly fine. So then you would do your integration. You get u to the 5 over 5. This would still be evaluated at x equal 1 and x equals 0. And then you could turn your u value back into an x value, because what was u? It was x cubed plus 2. So we'd have x cubed plus 2 to the 5th over 5. And now we could say that's evaluated at 1 and 0. Now that we're back to x values, it's safe to just write 1 and 0 there. And so our final answer would come out the same. It would still look like 211 over 5. So you can check that. So sometimes students prefer this alternative way. Sometimes it just feels like a bit less work to not convert the values over to u values. So you are free to do it this way. For some problems, this method will take longer, and in rare cases, it will take quite a bit longer. So I'm going to stick with the top approach where we do switch the values over, but as I said, feel free to use this approach if it seems easier to you. Here's our next example. So again, we're going to substitute u to try to make this integral easier. And you want to let u equal the quantity that's being raised to the power. So that would include anything that's sitting under a root. Let's let u equal x cubed plus x to the 6. So we'll figure out our du. Well, du by dx would be 3x squared plus 6x to the 5th. We could multiply that by dx. So just put brackets on here. Du is 3x squared plus 6x to the 5th times dx. So now this is where we look back at our integral and we figure out what we've accounted for already. So this square root here, we're going to be able to call that root u. So that looks good. But the other stuff that we've got in the integral, let's maybe circle it. We've got x squared plus 2x to the 5th times dx. So we're just going to ask ourselves the question, what is this equal to? What is x squared plus 2x to the 5th times dx? And the answer is almost always some multiple of du, right? So we just have to figure out, what do we have to multiply by? Or you might ask on the right side, what do we have to multiply or divide by to turn the second last line into the last line? Well, if we divide by 3, that would work. So this will be du over 3. So last thing we need to do here is just change our x values over into u values. So the x values on our integral were 0 and 1. And let's switch these over to u values. So to do that, just look back up at where you decided what u was x cubed plus x to the 6. We'll just plug our x values in there. So if x equals 0, then u is 0. And if x equals 1, then u is 2. So I'll put all this stuff in a box, as this was our process of just getting the integral rewritten, and then we can go ahead and rewrite it. So let's do that down here. So our integral is going to become the integral from 0 to 2. Our integrand, let's take a look at it. It's going to be root u times, we decided that this polynomial times dx together give us du over 3. So we can clean this up a bit and then just do our integration. So any constants like the 1/3 can move out in front. We've got the integral from 0 to 2 of, we might want to write the root u as u to the 1/2, and then that's times du. So we'll keep our 1/3 out in front, and let's find an antiderivative. So we're going to bump up the power, divide by the new power. So that's like multiplying by the reciprocal of the fraction. And remember, we don't need a plus c because we're doing a definite integral. We will evaluate at our u values, which are 2 and 0. Okay, now this is a situation that you'll see quite a bit where you've got a constant on the outside multiplied by a constant on the inside. So I would think about just moving all the constants to the front. It's like 2/9 times u to the 3/2, and that's going to get evaluated at 2 and then at 0. So we're going to have 2/9 times 2 to the 3 halves, because really when we evaluate the brackets, we've got 2 to the 3 halves minus 0. So a simpler way of thinking of that is just our 2/9 that we've got out in front times our 2 to the 3 halves. So the way that might be written in a final answer, just multiply the 2's together and say 2 to the 5 halves over 9 for our final answer. So let's try another of these definite integrals where substitution is involved. We're going to let u be the quantity that's being raised to the power. So that would be everything under the root. That would be our 6x plus 1. So du by dx then is going to be 6, and that means that du is equal to 6 dx. So then we can look up at our integral and we can say, well, we don't have 6 dx, we just have dx. So let's move from this line and just divide both sides by 6. Du over 6 is the same thing as dx. All right, then we'll change our x values over to u values. The x values on our integral were 1 and 2, and we're going to switch these over to u values. Okay, so look up at the top where you decided what u was, and we can plug in here. So u is going to be 7 and then 13. So put all this stuff here in a box. Those are all our ingredients for rewriting the integral. And then we can go ahead and rewrite everything. So I think I'll just do that right towards the bottom here. Our integral will become the integral from 7 to 13. Let's look into the denominator first. This 1 over the square root is going to become 1 over root u. And then the dx is the same thing as du over 6. So that way we've got everything rewritten there, and we can now scroll down. We don't need to look back at the original integral anymore. Okay, so let's clean this up a bit. The 1 over 6 can definitely come out in front. We're integrating from 7 to 13. We can rewrite this 1 over root u as u to the minus 1/2. And then the differential always gets written right at the back of the integral. Okay, so we'll keep our 1 over 6 out in front. Integrating the u to the minus 1/2, the power bumps up, becomes u to the 1/2, and then divide by that new power. Dividing by 1/2 is like multiplying by 2. And then this is going to get evaluated at 13 and then at 7. So another of these situations where you've got a constant out in front that's being multiplied by a constant inside, feel free to just move all the constants to the front. So that would be 2 over 6, or we might as well just call that 1/3 that's sitting out in front there. Okay, and then we're going to be subbing 13 and 7 into the square root and just subtracting. So let's say this is 1/3 times root 13 minus root 7. And that's our final answer there for the value of our definite integral. So let's try another one. Again, we're going to make a substitution. We're going to let u be the quantity that's being raised to a power. And then we'll work on finding du. So you could say du by dx would be just the derivative of x plus 1. That would be 1. And so that means du is equal to dx. So let's look up at our integral for a second. That means the 6 power, we're going to be able to call that u to the 6. So that's great. This dx, well, dx and du are actually the same thing in this particular problem. So that's taken care of. But this is a little weird. We got this factor of x here. So we need to ask ourselves, what is x equal to? Well, all we have to go on is just this information here that we've got in the box. So our du is actually not going to help us here, but what will help us is the way that we defined u. We said u is equal to x plus 1. So that means x is actually equal to u minus 1. So that's a little tricky. We haven't had to use that strategy before. It's something that comes up occasionally. Occasionally you'll need to look back up at u and figure out what one of your factors looks like in terms of u. So that allows us to say this part here is going to be u minus 1. Okay, the other thing that we need to do is just switch our x values over. So in our integral, we had x values -1 and 0. So let's switch those over to u values. And we're just Again, going to use the idea that u is equal to x plus 1. So we'll sub into that. Our u values become 0 and 1. So let's rewrite our integral and see if it looks better after we do the rewrite. So we'll just rewrite our integral down here where we can still see the original integral. So our u values are now going to become 0 and 1. We decided that this factor of x here is going to become u minus 1. The 6th power that we see in our integral becomes u to the 6th. And then the dx we said is the same thing as a du. Okay, so let's understand why this integral that we've just written down is easier to work with than the integral that we started with. So if you look at the integral that we started with, if you wanted to actually expand this out, you would need to multiply out the 6th power of x plus 1. So this part here is really not fun to expand. You could do it, but it would take quite a long time. So our substitution has just made kind of a subtle shift in the integral. Think about now what it would be like to expand this out. That wouldn't be bad. Our integrand would become u to the 7 minus u to the 6. We can integrate that, no problem. So our substitution has actually caused the integral to become something much easier to work with. Okay, let's just try to simplify our integrand here. Just actually expand it out. You'd have u to the 7 minus u to the 6 times du. And yeah, looks like we're good to go. We can integrate that and plug in and we'll have our number. So finding our antiderivative, u to the 8 over 8 minus u to the 7 over 7. We're going to first plug in 1 and then we'll plug in 0. So subbing in 1, we would have 1 over 8 minus 1 over 7. And then we're going to subtract off the value that we get when we sub in 0. That would just be 0. Okay, so in other words, if we create a common denominator here, you could say this is 7 over 56 minus 8 over 56. So our answer is minus 1 over 56. Now something kind of interesting happened in this example, and that is that our number came out negative. In our previous video, we said that what a definite integral does is it calculates the area under a curve. So you might ask, why would this area be negative? The area actually is negative if the curve dips below the x-axis. So let's draw a picture here and just understand the geometry. I'm going to scroll back to our original integral just so we remember what the question was. To integrate the function x times x plus 1 to the 6th, to integrate that from -1 to 0. So let's actually make a graph of this function here, just this highlighted stuff, and we'll see what that looks like. So you could do this on Wolfram Alpha. That's what I use to generate the graph, but I'm just going to draw a quick picture here just to show you what's going on. So we're interested in this particular function, which is our integrand, and we're interested in what it's doing just between -1 and 0. So at -1, at x value -1, our y value is 0, and at 0, our y value is 0. So our function passes through those 2 points. And it does this kind of thing. It increases up to this point, it dips down, comes back up through that point, and then it increases from there. Two more examples to go to finish off this video. So our next job is to evaluate this definite integral. Well, there is no substitution required here. We're going to see if we can find a different way to solve the problem. So the goal is to get this integrand simplified so you can get it into a form where it's easy to integrate. Now, if we just expand this out, that would work perfectly. So we'll just rewrite our integral. We're still going to be integrating from 0 to 1. We're still going to have our dx on here, but let's just FOIL everything out. So we'd have 2x minus x squared plus 6 minus 3x. And if you just do a little bit of simplifying here, the 2x minus 3x would just become a minus x. So I think I'll simplify right in this step just to avoid doing too much writing. So minus x squared plus 6 is our new integrand. And we can integrate that no problem. So let's find an antiderivative. minus x squared over 2 minus x cubed over 3 plus 6x, and we will evaluate at 1 and then at 0. Okay, so let's plug in 1. We'd have minus a half minus a third plus 6. So that all comes from subbing in 1, and then we subtract off the value from subbing in 0. Well, that's going to be 0. So let's put everything over a common denominator. We'll put everything over 6. So we got minus 3 over 6 minus 2 over 6 plus 36 over 6 gives us a final answer of 31 over 6. So just something to be aware of, that for some of these problems, you don't need substitution. You can just expand out the integrand and get the problem done that way. So let's try one more problem like this, where we just need to do something to our integrand. So let's evaluate the following definite integral. At first glance, you might try substitution. You might say, well, I'm going to let u be the quantity that's being raised to power. But if you take that approach, then you'll find that du is equal to something like 2x plus 2 times dx. And that's not going to work because you're not going to be able to find something that looks like du inside your integral. So this approach will not work. You can play around with it for a little bit to convince yourself of that. So there must be a simpler way. And the simpler way is just to recognize that we can fix up this integrand. So let's forget about the integral as a whole for now, and let's just focus on this square root of x squared plus 2x plus 1. Well, notice that this stuff under the square root is actually a perfect square. So we've got the square root of the square of x plus 1. X plus 1 all squared is the same thing as x squared plus 2x plus 1. Okay, so now we're getting somewhere. Now, flashback to pre-calculus. If you take the square root of a squared, you might be tempted to say that that's equal to a. But the truth is that it's equal to absolute value of a. Okay, so let's think about this. If you take the square root of 4 squared, for sure that's equal to 4. But the problem is, if you take the square root of something like, say, negative 3 all squared, that's not equal to negative 3. It's equal to positive 3. That's because square roots are always taking on non-negative values. So the square root of a squared is equal to absolute value of a. So while we would be tempted to say that the square root of x plus 1 all squared is x plus 1, the truth is that it's actually equal to the absolute value of x plus 1. So now we need to think about, well, what x values are we using in this problem? Remember that the x values are stored on the definite integral. So the x values in this problem are ranging from 2 to 4. If you want to draw a picture of this, that means when you're doing your integration, you only care about the portion of the x-axis where x is between 2 and 4. And so that tells us for sure x plus 1 is going to be a positive number throughout this problem. If you want to say this from an algebra point of view, x is ranging between 2 and 4 throughout the problem. So that means x plus 1 is ranging between 3 and 5. So for sure, x plus 1 is a positive number, and we can just say this is x plus 1. And if you had been in some situation where, say, x was ranging between, I don't know, let's say negative 9 and negative 8, then the absolute value of x plus 1 would actually be negative x plus 1. So this is really just for the sake of having a complete discussion of algebra skills. So that is now going to allow us to rewrite our integrand. We're going to fix this up, and then we will be able to do our integration with no problem. So we're integrating from 2 to 4. We've just decided, based on this discussion in the box here, that our integrand can be rewritten just as x plus 1. Put brackets around that, so we'll have x plus 1 dx that's being integrated. Okay, let's go for it. Finding an antiderivative, x squared over 2 plus x, and we'll evaluate that at 4 and then at 2. Just subtract those values. So plugging in 4, we would have 12, and then we subtract off the value when we sub in 2, which is 4. So 12 minus 4 gives us 8 for the final value of our definite integral. So bottom line with these definite integral problems, first ask yourself, is there anything I can do to get the integrand into a form that's easier to work with? If that doesn't work, then use substitution. And if you want to use the substitution approach, remember that your x values should be changed over into u values. So that's all about definite integrals using the substitution method. Thanks for watching.